There's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones were little,
Little.
they're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right? And essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon, and if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now. So we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know then, there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses. And that's when you get a black hole.